Hello and welcome. In this second part of the video, I'm going to go through the same examples only with a slightly different method. It's slightly more explicit in making the assumption clear and clearly shows the factorizations that we are doing. So it's not a huge difference, but if you like to watch this video and perhaps you like this second method, then it might make your life slightly easier. So let's go through it. Hello and welcome to this video. In this video, we'll be looking at proving the divisibility of certain formulas with induction. As with other induction proofs, we always have four stages. We start with the basis. That would mean for us to substitute number one and prove that our formula works for number one on both sides of the equation. Then we assume it works, or the formula is divisible for a certain value of k. So we substitute the k for n into the formula, and we want to show that it will take us up one step and it will hold for f of k plus 1. If it works for f of k plus 1, then we can go to the conclusion and say that the formula works for all positive integers. All right, so let's start with a real example. In this formula, we've been asked to show that 3 to the power of 2n plus 11 is divisible by 4. So we take our base for our basis step. Okay, so that's step number one. We're going to say that n equals to 1. So 3 to the power of 2 times 1 plus 11. And we're going to work it out. So 3 to the power of 2 is 3 squared is 9, and 9 plus 11 is 20, and 20 is clearly divisible by 4. Therefore, our basis step holds for this equation. So then what we're going to do is move on to the assumption step. Now, the assumption step is the easiest part, I believe, because we don't have to do a lot of work. We are just assuming that the formula works for some integer value k. Now, this k is on doesn't need to be a specific number as long as k is an integer. So at this stage, we actually making an assumption that this formula, this form, is divisible by 4. So therefore, we can write it as 4 multiplied with yet another number. Now, m, as long as m is an integer, that's all that's important, and that's all for now. Okay, so then what we're going to do is move on to the, so our assumption step here is complete. So we're saying that this is indivisible by 4. Now, for inductive step, what we can do, we need to clearly indicate that we are moving up to the inductive stage. So we are going to say that substitute k plus 1 into the formula and look at what we will get. We will have, instead of k, we're going to have use a bracket here and write k plus 1 wherever the k was, and write the rest of the formula. Now, when we expand that bracket, we were going to have 3 squared, because this 2 is multiplied by 1, multiplied by 3 to the power of 2k. I'm just expanding the bracket there and writing the rest of the formula. We clearly know that 3 squared is a 9. Now, at this stage, what we have is an extra 9 in front of 3 to the power of 2k. What we can do is we can go back to I left the tiny gap here, so I could actually rearrange this. We can see from our inductive assumption that 2 to the power of k could have been written as 4m minus 11. So I'm just taking this plus 11 and removing it from the left hand side, put it on the right hand side as a negative 11. So now what we can do is use this 4m minus 1 where I've underlined 3 to the power of 2k. And what I can substitute that with, replace that with, is 4m minus 11. And I will continue writing the rest of the form as it is. Now, upon expanding, I'm not going to actually write 9 times 4 is 36. I'm going to swap 4 and 9 around and just write 4 times 9m and write 9 minus 99 plus 11. Now, I've expanded the brackets on the line above, and we can now clearly see that 99 and minus 11, sorry, negative 99 plus 11 make a negative 88. And now we can factor a 4 out of 88 and the other term at the front and write 4 multiplied by 9m. Now I started writing capital M and then I replaced that with a little m. I should have kept it in the same form, but m is m in this case, so my apologies for that. I should have kept writing capital M everywhere. So now I have to divide this 88 by 4, which is 22, and this is clearly f of k plus 2, and we have shown at this stage that it is divisible by 4 because 4 was factorized out of the expression. So here we can tick the inductive stage, and we've done that, and we can write a conclusion that the algebraic steps worked for n equals to 1, and it also worked for, you should actually really write a more specific proof that when you're writing a conclusion, you should actually write the word conclusion and say the formula worked for n equals to 1. We assume that it worked for k, and also formula worked for k plus 1. Therefore, by inductive hypothesis, by induction, we've proved that we have shown that the formula works for all positive integers, or rather the form that we were given, formula is divisible by 4 for all positive integers. Okay, so let's have a look at the next example there. So in this question, we've been asked to prove that the formula n cubed minus 7n plus 9 is divisible by 3. So we make the basis assumption, but basis step, and substitute n equal to 1 into the equation. This is rather simple. So 1 minus 7 plus 9 is negative 6 plus 9, which is not 3, and that's obviously divisible by 3. So we're moving on to the assumption step here. So we are substituting k where the n was. So we can write f of k where our f here was in terms of n and now is in terms of k. So we are making an assumption that this formula, or rather this number, when evaluated, is divisible by 3. That means it has a factor of 3. So we can write that as equal to 3m. Then at the inductive step, we're going to substitute k plus 1 where the n was in the original formula. So if you are not familiar with binomial expansion, please go and find my video on binomial expansion, because here we have to multiply out a bracket, k plus 1 is raised to the power of 3. So here you can say that k to the power of 3 plus 3 times k square plus, well, there is a times by 1 there, but I'm not writing it, and also 3 to the power of k. There's a 1 raised to the power of 2, which I'm not writing, and finally we'll have a plus 1. Then we'll have a 7k, negative 7k minus 7 plus 9. Now collecting like terms, this negative 7 and plus 3 are, we can simplify it, but I'm going to leave this k cube here. There is a extra factor of, okay, let me just write this as, this will, the two terms I underlined, they give us negative 4k, and the squiggly lines are going to give us plus 3 there, because 10 minus 7 is plus 3. Now, at this stage, we cannot directly use our form there. So we see that we have these terms, but well, not in. We only have the k to the power of 3. So we can do some rearrangement of this line here and write k to the k cube there. We don't have a 3k square, but luckily that has a factor of 3 already in front. So we can keep this negative 4k. In maths, there is always the trick that you can add and subtract anything you want. As long as you add and subtract it in the same line, that will keep the equation balanced. So what I'm going to do is add and subtract the plus negative 3k. So I'm going to write the negative 3k here. That would give me a negative 7k. And I'm going to actually, because I have a plus 3 there, I'm going to keep that plus 3 and add a 6 there. Now, to make the equation balanced, you see that I obviously cheated and I added these two terms so that on the next line I will have what I want. But to make it balanced, obviously we need to add a 3k and take away a 6. Now I'm not going to forget there is also this extra, this line had a 3k square there, so I'm going to keep that there as well. So at this stage I've simplified these terms that I'm putting a bracket under them, and I've written it there, and I can factor a 3 out of these extra terms that weren't in the original f of k, and I can factor a 3 out of them and write it like so. So what we did was that in the assumption step, we said that k cubed minus 7k plus 9 was divisible by 3. And we could use this letter if we want to. And now we have an extra factor of a 3 in front of this other bracket, which I could have put rearranged, but I'm going to leave it as it is now. So finally, I can factor 3 out of everything and say that we have shown that everything has a factor of 3. Therefore, in conclusion, we can say by inductive, we have proved that our formula holds for all positive integers k. Okay, so let's look at yet another example here. So in this question, we've been asked to prove that this formula is divisible by a large number, 133. So first of all, we set up our stages of proof. This basis involves a basis stage, and then make an assumption and use it. So for basis, we're going to say that n is equals to 1 and evaluate the formula with value of 1 in it. So let's have a look at that. For the basis, we're going to have 11 to the power of 2 which is 121 plus 12. Because we are going to take away 1 from 2, there is just a plus 12. So 121 plus 12 is exactly 133, and that is clearly divisible by 133 because it's times by 1. So now we are going to tick the basis step off, and we're going to go on to the assumption step. So we are going to just write the same formula with the value of k substituted for n. We're not going to evaluate it or rearrange anything. What we can do at this stage is to say that this form is equals to 133m. Now m can be any number as long as it's an integer. It's we factorized 133 out of it for our assumption. So now what we're going to do is use the inductive step and substitute k plus 1 wherever the n was in the original formula. So if you look at it carefully, we're going to use a bracket where the value of n was. So we'll have 11 raised to the power of k plus 1 plus another one. So I'm just going to write plus 2 here actually. And we are going to have plus 12 times 2 to the power of k plus 1 minus 1, because that's what's there. I'm replacing n with k plus 1. So evaluating this, what I'm going to do is, because I have a n in my assumption step, I have a k plus 1. So actually, I'm going to factor this 2 out and write it as 11 times 11 raised to the power of k plus 1, because that's what it means when we raise 11 to the power of k plus 2. And then what we are going to do is, if we multiply out this bracket here, we will have 12 raised to the power of 2k plus 2 minus 1. So I'm just going to keep the minus 1 first, and I'm actually going to write, instead of plus 2, I'm going to write 12 to the power of 2, because that's what plus 2 in the index means. Now, we know that we have 11 over here, and 12 square is 144. So I'm going to write this one more time. These lines are equal to each other. So perhaps it would have been better if I actually wrote k plus 1 on this line here. It would keep everything clearly written there. So I'm going to multiply this 12. I'm going to write here 11 times 11 raised to the power of k plus 1. I will have 144 multiplied by 12. I'm rewriting that in front here. So times 12 raised to the power of 2k minus 1. And at this stage, we are going to say that we're going to split this 144 up into 133 plus 11, because, well, I see an 11 in front of this 11 raised to the power of k plus 1, and I want to factor an 11 out of, let me write it. Writing this proofs takes a bit of time, so I'm actually going to take a little bit longer than I need to, and write this as 11 times 12 raised to the power of 2k minus 1 plus this 144. Basically, I'm writing 144 as 11 plus 133. Okay, so I'm going to put 133 here multiplied by 12 raised to the power of 2k minus 1. Now, by I can factor 11 out of this. When I factorize an 11 out of this, I will have what I had in my assumption step, which is 11 raised to the power k plus 1 plus 12 to raised to the power 2k minus 1. And this extra factor of 133, luckily, in front of 12 raised to the power of 2k minus 1. Now we can say that by assumption, we said that this bracket in the hypothesis, in the assumption step, these underlined lines are exactly the same. So that was already a multiple of 133m by assumption, and we have yet another 133 in front of 12 raised to the power of 2k minus 1. So we can swap this basically, instead of multiplying this number out, just going to bring out 133 and put 11 inside the bracket, multiplying that bracket. And let me rewrite this. I'm going to take my time and write everything in as many lines as it takes. So now I'm going to factorize 133 out of both terms and write here that's 11m, and there is a plus 12 raised to the power of 2k minus 1. And by inductive hypothesis and inductive step, we've shown that this formula holds for all positive integers k. Now you might want to write that down in words actually, rather than saying it. So yes, please take your time when you're writing proofs and write a conclusion and make it clear that to the examiner you know what you're talking about. You say the formula held for n equals to 1. Formula was divisible by 1, by divisible by 133 rather, for n equals to 1, and by induction we proved that it is also divisible by 100. It also holds, is also divisible for k and k plus 1. It is divisible by, it holds for all positive n, or positive integers. Positive integers. Okay, I hope you find this helpful, and I wish you the best with practicing this, and I'll see you in another video.